Good morning everyone. I am Professor Chetan Mistry from IIT Kharagpur, Department of Aerospace Engineering. I welcome you all on second day of Gyan program on Aeroelasticity and Unsteady Aerodynamics in Turbomachinery. Now today we will be discussing more in terms of aerodynamics of compressors and turbines and what we say in terms of unsteady flow. So if we look at, the question will arise in our mind, say why we are having this kind of course or why we need to have the understanding of this unsteady aerodynamics, what are the causes for this unsteady aerodynamics, and the thing is how you can resolve. So if we look at the recent trend, especially for aircraft propulsion, major concern is with the weight to thrust ratio and as per the requirement of pollution regulation as well as for specific fuel consumption. So we are looking for aircraft engines which are lighter and compact engines. So that's what is required, a special kind of materials. We are using composite materials, and that's the reason why we are having constraint with the structural integrity margins. Secondly, if we are talking in terms of thickness of our aerofoil, or maybe if we consider the thickness of the trailing edge for the rotor, if we change the thickness by 0.1 mm, it will give you 0.1% specific fuel consumption as a penalty. Other constructive measure, if we consider, that's what is in terms of weight. So in order to address weight as a constraint, what we need to do is we need to decrease the number of stages and the number of blades. That will lead to increase the loading of the individual blade, and also the axial spacing between this rotor and stator, that's also putting the constraint to us, which will lead to increase the dangerous aerodynamics load. When we are talking in terms of application for land based power plant, what is happening, our major concern is in terms of specific fuel consumption, and that's the reason why the load, and here we are having our constraint with the cost, and that's the reason why people they are putting more efforts towards the development of new engines. Now lifetime of the engine for these components, that's what is major play if we talk in terms of maintenance, operation and services. For that, cost is a major criteria. By reducing the maintenance efforts, we need to have we need to stay with the competitive world for the gas turbine engines. Now if we look at, we are having specific designs. If we look at, it is not like the compressor or the turbine what we have designed that we are using we can use for the other engine. It is not like that. So specifically we need to do lot of research and development activities for the development of these engines, and that's the reason why we need to have lot of data, experimental data along with us. So in overall, if you look at development and validation of this numerical tool for the calculation of structural and aerodynamic consideration, what we need to do, we are totally relying on semi-empirical relations. So yesterday what we have discussed in terms of aeroelasticity, Professor Maiti has given some highlight for that. Now the time has come where people they are looking for the design that need to be done very faster and at the cheaper rate, and that's what has motivated to carry on this kind of study, especially when we are talking in terms of unsteady aerodynamics for turbomachinery. Now yesterday Professor Maiti has discussed about Collar's triangle. That's what is comprising of mainly three forces, what we say inertia force, aerodynamic force and elastic force, and he has given some glimpse of that. Now today, after completing this course, all participants should be known the understanding of basics of the compressor, that's what is applicable. Many of the students, many of the participants, they are not having exposure of turbomachinery, and that's the reason why I am starting with some fundamental parts so that they can understand easily. Slowly we will be going towards the complexity in terms of three-dimensional flow field. Then we will be discussing operational instability in terms stall and surge, and flow instability, that's what is happening because of inflow distortion. So in overall, if you look at, this is what will be providing us the platform in terms of understanding the unsteady aerodynamics, and that will be discussed in detail by Professor Watanabe from tomorrow onwards. So if we look at the trends for the compression ratio, say during 30s and 40s, the compression ratio that's required in the range of 3 to 6. slowly that has increased, and now people they started talking in terms of say compression ratio of 40 to 50, and that's what is putting a lot of challenge for the designers who are those who are designing the axial flow compressor. So if we look at the target for present in terms, when we are talking in terms of say commercial aircraft, where people they are of more concern to say thrust specific fuel consumption. Over the year, if we look at this thrust specific fuel consumption, that's what is decreasing. At the same time, if you look at our engine configurations also are changing. Initially we were having say single spool turbojet engine, then twin spool, then people they started talking in terms of say turbofan. Now people they are talking in terms of high bypass ratio engine, and now people they started talking even for say propeller fans. So if you look at these two are the engines, this is just for the representation purpose. Say these are the GE engines. If you look at one, that's what is applicable to say aircraft engine, and second one, that's what is a land based power plant. So if you look at clearly, both they are having same components in sense they are having compressor, combustion chamber and turbine. So if you look at here, there is a very uncommon scene. If you look at the compressor stage, here in turbofan engine, if you look at, we are having big size fan that will be followed by say compressor stages, and later on if you look at the size of the blades, that's what is decreasing. When we are comparing that, specifically what I mean to say is in terms, say this is what is a region where we will be having say comparatively taller blade compared to our aircraft engine. That means in terms the requirement of compactness and lightweight, that what has attracted to have modification in terms of design, especially when we are talking in terms of say aircraft engine. And space and weight is not a criteria or not a constraint for our land based power plant, and that's the reason why the blading that may be somewhat different. If we talk in terms of their design, that's what is different. If we are talking in terms of making process, that's what is different. If we are talking in terms of say number of stages, those are different. So that's the reason why the thing is like we need to talk overall in terms of say gas turbine engines. Now here, this is what is a picture of say Pratt & Whitney engine. This is just for the representation purpose. If you look at, we are having big size fan, that's what is known as high bypass fan. That's what is being used to generate the thrust. Calculation roughly says like 70% of your thrust, that's what is being generated by the fan only for this engine. And later on if we look at this particular region, that's what is known as core engine, and that's comprising of LP stage, that is what is comprising of HP stage, and then we are having HP turbine and LP turbine. Now we need to understand when we say in terms of fan, earlier the definition for fan, it says that will provide large mass flow rate and low pressure ratio, but for present or recent engines, if we look at the pressure ratio, that's what is in the range of 1.6, 1.8, and that's the reason why the definition it seems not valid as such. Now if we look at here, this configuration is two spool configuration. So here this particular region, that's what is known as a LP spool, and this particular region, that's what is known as a HP spool. Now LP spool, that means you need to understand my operating pressure is low, and that's the reason why that's what is known as LP or LP compressor. My operating pressure is higher in HP spool or say HP, that's the reason why that's what is known as a HP compressor. It is not like HP compressor is generating more pressure. Okay. Now that's what is been connected on with shaft with fin spool, that's what is been rotated by HP turbine, and we are having say LP turbine. Now if you look at carefully what is happening, say when we are moving towards the downside or the rear side, my area, that's what is decreasing. The reason here, we are assuming our axial velocity of the flow, that's what is constant. And according to continuity, what it says, with increasing our pressure, our density is increasing. And in order to maintain our continuity to be satisfied, we will be having decrease in area. And that's the reason why we are having decreasing area. Same way, if we are talking in terms of say turbine, what is happening in turbine? We are having expansion work. During expansion, my pressure is decreasing. That means my density is decreasing. In order to maintain my continuity, my passage, if we look at that passage, is converging passage. Okay. Now here if you look at, if I will be taking one of the blade and if I take the cut section say at the mid section, then it will be looking like this. If we look at here, this is what is known as leading edge and this is what is known as a trailing edge. And this area, if you look at, that's what is area A1. Here this is what is my area A2. If we look at carefully, my passage area, that's what is increasing. That means we can say my passage is diffusing passage. Now my blade, you need to be careful. If I say my aerofoil I am using, that means the understanding will come, say all logic what we are applying for say our aerodynamics of aerofoil, cambered aerofoil, that is not straightway applicable here in the case of compressors or turbine. The reason here, if you look at, this is what is my say compressor blade. That compressor blade, it is comprising of number of aerofoils. They are being stacked about particular manner. So if you look at these all black lines, what says sections, they are made up of say different aerofoils. It may be same category, it may be different category. Similarly, this is what is known as stator. So now the situation is, what we want to do is we want to compress our air. So we need to do the work on our air or flowing fluid. So the logic for using aerofoil is to utilize your lift force. Here if you look at, I will be having my differential pressure across this aerofoil. This particular region, that's what is known as say pressure surface. This is what is known as suction surface. So on pressure surface I will be having high pressure, on suction surface I will be having lower pressure. So what will happen? I will be having lift force that will be generating, and here this blue arrow, that's what is indicating the direction of my flow. So if we look at carefully, my direction of flow, that's what is from suction side towards the pressure side, and my lift force, that's what is acting from pressure side to suction side. So we are utilizing our lift force for compressing our air. Now, so if we look at, this is what is a schematic for say multi-stage axial flow compressor. If we look at, it is comprising, as I discussed, of say rotor and stator combination. So if you look at, this is what is known as rotor stator combination, or in conventional way, that's what is known as say stage. Here this is what is known as say inlet guide vane. Now for inlet guide vane, there are different approaches across the Pacific. If we talk in terms of say European Unions, they are generally avoiding to have say inlet guide vanes. When we are talking in terms of American designs, they are preferring to have inlet guide vanes. They have different design philosophy. Now the purpose here for providing the inlet guide vane is to guide the flow towards your rotor. Here if we look at the stator, the purpose of the stator is to guide the flow to next coming rotor. Now what rotor is doing, as we have discussed, we are having diffusing passage. So rotor, that's what is diffusing my flow, and from there my flow that will be coming out, that will be striking on my stator. That stator will guide the flow for the next rotor up to certain say aspect. I say this is what is applicable. Later on you will realize stator also has to do diffusion work. Now, so let's try to understand very important part when we are talking in terms of turbomachinery. That's what is our velocity triangle, and the understanding of this velocity triangle, that's what is always very important. If we look at here, this is what is my stator and this is what is my rotor, and this rotor, that's what is rotating from suction side towards say pressure side. If we look at my flow, that will be coming out with some absolute velocity say C2. Now because of my rotational speed, if I consider and put the vectorial part, what it says, my absolute component is relative velocity plus my peripheral speed. That's what will give me my relative velocity. So this is what is my relative velocity. Okay. Now if I put, this is what is representing my absolute velocity lines. Similarly, here if you look at, this is what is representing my relative velocity lines. Now, when we are talking in terms of stator, we are talking about absolute reference frame. When we are talking in terms of rotor, our reference frame, that will be relative. Now, if we look at, say, this is what is my blade, as I discussed. For that blade at midsection, let me put my velocity triangle. This is what is my velocity triangle if I consider my flow, that is what is entering axially. This is what is my rotational speed for the rotor, and this is what is my relative velocity. This beta 1, that is what is known as my blade angle. Now, my flow that will be coming out with relative velocity V2, with reference to my axial direction, I am having my exit flow angle, that is what is B2. If I am putting my speed, rotational speed or peripheral speed, that will give me my absolute velocity component, that is what is C2. And this C2, that will be striking on my stator, and that will come out axially. So, this is how my velocity triangle, that is what is working. This is what is very important when we will be talking in terms of performance, in terms of understanding, say, instability in axial flow compressor. So, you need to remember this velocity triangle, and if you look at the passage here, for rotor, as I discussed, my inlet area, that is what is lower, my outlet area, that is what is, say, larger. Similarly, for stator, same is the situation. Now, as I told, say, my blade, that is what is comprising of, say, number of aerofoils. So, at each aerofoil you will be having variation. Why it is having variation? Because if I am defining my peripheral speed, that is what is known as, say, pi d n by 60. As my diameter or my radius is increasing, my peripheral speed is increasing, and accordingly my blade angles, that will be changing both for rotor and stator. Now, this is what is our fundamental equation based on, say, Euler's equation. What it says, my work done, that is what is given by U into Cw2 by Cw1, that is what is been represented in terms of angles. Now, what we have understood from our thermodynamics, that is what is been represented in terms of, say, enthalpy change or total enthalpy change, that is what is given by mCp T02 minus T01. So, we will be having two kind of work. Aerodynamics, they are representing that based on, say, Euler's equation. Thermodynamics, they are representing that in terms of, say, thermodynamic work. Both are same. Now, if I am representing that my work done in terms of my pressure ratio, then that is what is given by pressure ratio, that is what is given by my efficiency, my total temperature rise and inlet temperature. Now, the question is, as we have discussed, we are talking about the recent design where we are expecting our compressor or rotor or stator stage that need to produce larger amount of work. Why? We want to have, say, smaller number of stages, low number of stages, because we are looking for compact design. And at the same time, when I am decreasing the number of stages, I am decreasing my weight of stator, weight of rotor. That means overall penalty in terms of drag we are decreasing. Okay. Now, if we want to increase this pressure rise, based on this fundamental equation only, you can understand I need to increase my delta T0. This delta T0, what it says, I can increase by increasing the rotational speed. Suppose, say, I am increasing my rotational speed u. If I am increasing my rotational speed, you will understand my flow that will be becoming supersonic at particular region, and that is where I will be having problem. That is what is in terms of, say, structural problem. So, Professor Watanabe, he will be discussing few things in that highlight. Okay. What we are talking in terms of, say, aeroelasticity for the blade when we are talking in terms of high speed application. Similarly, if you will be talking in terms of high axial velocity, what is happening? You will be having, say, supersonic flow, because now your radius, that is what is changing. what you need to do is, in order to accommodate, when I say my axial velocity is increasing, that means my mass flow rate is increasing. Accordingly, my frontal area also I need to increase, and that is what is the problem in terms of, say, you will be having shock patterns to be formed, and that is what is creating blockage to my flow, and that is what is giving me aerodynamic penalty. Next option what we are talking, that is what is in terms of, say, deflection angle. That is what we are defining as beta 1 minus beta 2. Suppose if I will be having larger delta beta, you will be having larger work done. But the thing is, since we are working under adverse pressure gradient, what is that adverse pressure gradient? My inlet pressure is lower, my outlet pressure is higher. That means I am working under adverse pressure gradient. There are more chances for the flow separation to occur. So, if we look at how my flow that will be behaving on my aerofoil, this is what is for general representation purpose only. If we look at, this is what is a region, that is what is known as leading edge. Somewhere here I am having stagnation point. Now that stagnation point, that separates, or that will permit your streamlines to move on upward direction as well as on downward direction. What will be happening? Since infinitely long distance I will be having parallel streamlines, so this particular region that will be acting like a nozzle, and that is the reason why we are having rise of velocity up to certain distance. What will happen according to your Bernoulli's equation? It says when I am increasing my velocity, my pressure that will be decreasing. Now here it is very interesting to say, like your suction for your compressor, that is what is happening by this action. There is no extra additional mean that will give the suction of air, because it need to suck the air from the atmosphere. Now what is happening? Now if you look at, we are having this shape, that is what is like diffusing shape, that is what is acting like the deceleration of my flow. So this is what is my deceleration of flow, and accordingly I will be having rise of pressure, and that is what is our requirement. Now this is what is showing my distribution of inlet pressure and outlet pressure. On blade, later on we will be discussing what is happening. Now there are different types of aerofoils, as we have discussed. If we will be putting, say, one plate, and if we will give the curvature, that also will give the rise of pressure. But the thing is, that pressure rise is not as per our requirement. In that case, we need to take the benefit of, say, this aerofoil shape. So here if you look at these aerofoils, they are subsonic aerofoils. So in that we are having NACA 65, we are having C4 aerofoil, that is what is known as, say, your British aerofoil. Most of the low speed application designs, those aerofoils, they are being made. If you look at, this is what is my blade, and for this blade, this aerofoil what we are talking of, that is what is my C4 aerofoil. Similarly, if you look at, this is what is my next blade. This blade, if you look at, and if you compare these two different blades, this blade is thicker blade and this blade is thinner blade. Later on, very soon you will understand what is the reason behind it. This blade, that is what is transonic blade. So if you look at, for transonic blade, we are having, say, this is what is my case here. This is what is specially been made, that is known as, say, double circular arc, multiple circular arc, and maybe S type of blade. So over the year, as per the requirement, people, they have modified their shape and they are using this kind of aerofoils for transonic rotors. Now let us try to understand. Once you understand this part, half of work, that is what has been done in terms of understanding your compressor. Okay. Now here if you look at my flow, that is what is entering from upside. Here I am having my leading edge, this is what is my trailing edge. As I have discussed, lower part, that is what is known as, say, pressure surface, upper part, that is what is known as, say, suction surface. Now what is happening? When my flow is entering, Here this is what is been represented in terms of velocity, my acceleration of flow, and later on my flow, because of curvature of my blade, that is what is getting decelerated smoothly. Similarly, what is happening near my pressure surface, I will be having particular small region, I will be having my acceleration of flow, and then after my flow, that is what is getting decelerated, and this is how my velocity distribution will be. Conventionally, for turbomachinery, people they are defining their performance in terms of Cp. If you look at, this is what is the Cp distribution as I discussed for subsonic aerofoils, say C4 aerofoil, for DCA, for NACA 65 aerofoil. If you look at, this is what is a region what we say in terms of my pressure surface. So, on pressure surface I will be having strong acceleration, and then after nearly constant pressure you will be achieving. Now, what is happening on my suction surface, I will be having my acceleration of flow, and then after my flow is getting decelerated. Now, let me tell you, this Cp, that is what is deciding like what is my pressurizing capacity of compressor. Suppose if I am talking of, this is what is at mid section, means this much amount of pressure rise, that is what is been happened by my mid section. If I am talking in terms of overall blade, I will be having summation of this all Cp, and that is what is giving me total pressure rise. Okay. Now, Americans they have done lot of experimental work on Cascade, and they have defined one parameter, that is what is known as say diffusion factor. That is what is based on these fundamentals. What they say, they are having maximum acceleration possible, that is what they have defined as V maximum. My inlet velocity is V1 and my outlet velocity is V2. Let me discuss here in terms of my velocity triangle. Here if you look at carefully, this is what is my inlet velocity and this is what is my outlet velocity. Which velocity? I am talking about the relative velocity. Now, if you look at carefully, their magnitudes are different. Now, at the exit, I will be having my relative velocity to be lower. Okay. And that is how they have defined this as one of the parameter. They have plotted that with say friction losses. What that indicates, for rotor, hub or for stator, my loss coefficient, that is what is remains constant for my diffusion factor in the range of 0.4. If I will be having my diffusion factor to be large, then my loss that will be increasing. And they have put the constraint in terms of having say diffusion factor, they say that need to be in the range of 0.5. But now with the change, with the understanding of physics, with using numerical tools, people they are talking in terms of diffusion factor larger than 0.5. Now this diffusion factor, that is what is incorporating solidity, that is what is known as chord by say pitch. Pitch in the sense what is the distance between two successive blades. So, here if I look at this point and this point, that is what is we are defining as a pitch. That is what is depending on my number of blades. You can look at 2 pi r by z, and secondly that is what we are talking in terms of say chord. Okay. Now, the situation is, as I told, I need to have higher diffusion, then you need to play with these parameters. Suppose if I am talking, if I will be having my hub diameter to be smaller, my tip diameter to be larger. If I want to accommodate my blade, I can say I will be having less number of blades I can accommodate. What is the reason? Because my hub, that is what is having constraint. I cannot accommodate more number of blades. Now, suppose if I am talking my hub diameter comparatively larger, what will happen? I need to have more number of blades. So, similar situation you are observing in engine. Suppose if I am talking in terms of say HP, if I am talking in terms of LP, if I am talking in terms of fan. Fan is having this kind of configuration. When I am talking in terms of HP and LP, they are having this kind of configuration. One important parameter what people they are talking, that is what is known as say degree of reaction. This is what is important parameter need to be understand being a designer, but still when we are talking in terms of three dimensionality of flow, this fundamental concept, that's what is required. What we say, if we are talking in terms of say my degree of reaction, that degree of reaction, that's what is defined as my enthalpy rise in rotor divided by my enthalpy rise in stage. So, if we are talking in terms, suppose say I have my degree of reaction to be 0, what it indicates, my enthalpy rise especially in rotor, that is what is 0. So, if you look at my pressure rise in my rotor, that is what is almost constant, I am not having any pressure rise. Then what is my requirement? I want to use my compressor stage for the pressure rise, then hold my compression, that is what is happening in stator. So, if you look at from 2 to 3, that is what is representing rise of my pressure. Similarly, I am having other kind of design, that is what is defined as a degree of reaction to be 50%. So, 50% pressure rise, that is what is happening in rotor, 50% pressure rise, that is what is happening in my stator. Okay. Now, if we look at I am having say 100% reaction, that means whole my pressure rise, that is what is happening only in my rotor, no pressure rise, that is what is happening in my stator. Now, no pressure rise in the sense my flow need to pass without any acceleration or deceleration. This seems to be simple in that sense when we are talking in terms of having degree of reaction to be 0 and my passage area, that is what is constant. But in actual practice, if you look at when my flow, that is what is flowing through my blade, because of my viscous effect, I will be having growth of boundary layer, and that is the reason why in the later stages you will find my passage area, that is what is decreasing. That means rather giving my smooth flow or without acceleration or deceleration, it will give you accelerated flow. So, that is where the designer he need to take care of. Most of the German design people, they are talking in terms of this kind of configurations. Now, new concept people, they are talking in terms of say tandem configuration. This is not new concept, people they have explored during 1960s, but because of understanding in terms of say flow physics and the complexity of the flow, the work that has not been extended. Now, again people they have shown their interest towards the tandem configuration. If you look at, this is what is my rotor, this is what is my stator, I have rotor and stator. You can understand I am having two stages. What we have discussed, we want to decrease the number of stages. Now, in order to decrease the number of stages, what we need to do is we need to do more amount of work by the stage. Now, in order to do more amount of work by the stage, what you need to do is you need to change your delta beta. So, here your delta beta, and here if you look at as overall one blade, that delta beta, that is what is different. Now, if you want to have look at, this is what is a blade, that is what is say your tandem configuration. What is happening if you look at this as a single blade, this is what is single. Okay. Here this is what is my single blade, this is also single blade, but the thing is we are having tandem configuration. What it means, now here if you look at the curvature of my blade, that is what is larger, and that is what is required to achieve more pressure rise. Now, the thing is why it is having interest is in terms of having your configuration in terms of say more pressure rise. Okay. Now, what concept people they are talking in terms of this tandem configuration is, suppose if I will be having larger curvature, there is a more chances for my flow to get separated from the suction surface. Since we are having additional blade, that is what is being placed below this. What exactly it is doing, because of this gap between these two blades, what will happen, my flow that will get energy from this particular region. Here this leading edge, that is what is accelerating my flow, and that is what is giving more momentum to my flow, and that is how I can delay my flow separation that's what is happening on my blade. Okay. By doing so, now what is happening? Now I need to enter my flow to next stage in say axial direction. So I will be having my stator configuration, that's what is of impulse type. And here it says this much amount of length we can save. Roughly people they are talking in terms of 30% reduction in say the length of my engine. Now when we say 30% reduction in length, that means it's a length of my stage and it's a length of my shaft on which I will be putting my rotor. So if we look at that shaft, suppose if it is a solid shaft, the weight you can consider. Considerable amount of weight you can reduce by incorporating this. Okay. So here if you look at, we are having the reduction, overall reduction in weight as well as overall reduction in the size. Now let us try to understand what kind of flow, that's what is happening in our axial flow compressor. So here if you look at, this is what is my particular region. Now my casing in which I will be putting my stage, that's what is a solid body. Now for that solid body, what is happening? This is what is solid body, that is having say growth of boundary layer along my length. So if you look at, this is what is my growth of boundary layer. The growth of boundary layer that will be happening near casing, growth of boundary layer, that's what is happening near the hub also. Now if you look at carefully, this growth of boundary layer we can consider that will be acting like a solid body. So we need to have our passage to be diffusing passage. Now here if you look at, that's what is converging passage. So now you need to understand, we have two processes, they are going parallelly. One is diffusion process, second that's what is my say acceleration process. Okay. And that's what is making whole my physics or inside my flow, that will be 3-dimensional flow. Now near the tip region, we know we need to have certain amount of clearance to be provided between casing and the rotor. Now when we are providing the clearance, what is happening? My flow always will be having tendency to move from high pressure side to low pressure side. So this is how my flow that will be jumping. Okay. So if we look at near the rotor region, I am having growth of boundary layer along my casing, and I will be having jump of my flow in this region, and that's what is giving me complexity. Now the same flow, that's what is moving towards the stator, that means it will change the performance of stator also. Now here if you look at, this is what is representing my axial velocity over the stages. Now when we consider over the stages, what is happening? We are assuming our axial velocity to be constant throughout my stage, okay, throughout my compressor. But because of growth of boundary layer, what is happening? My velocity that will be having deficiency. So this is what is my deficiency in the velocity. Now as we have seen, my work done, that's what we are representing as u Cw1 minus Cw2, that I can represent in this way also. What this indicates, since my axial velocity is decreasing, so I will be having my increasing work capacity near the hub and the tip region, and that's what is decreasing my working capacity. That means if you consider, if we are assuming at initial stage of the design my axial velocity to be constant, and when we are checking with the performance on say test rig or maybe on real engine, it will not give me what pressure rise I was expecting. Okay. So this is what you need to care for. Now in terms of, when we are talking in terms of say prime movers, basically we are talking in terms of losses. This losses we are differentiating in terms of aerodynamic losses and mechanical losses. This mechanical losses, that's what is not in the scope of this course, so we will not be discussing on that. Let us talk in terms of say aerodynamic losses. If we talk aerodynamics loss, we say we will be having 9%, around 9% loss, that's what is happening in the rotor. 89% that is what is in terms of my stator. So, if you look at in terms of say my aerodynamic losses, it will be secondary loss, profile loss, annulus loss, tip leakage loss, shock loss. Okay. Similarly, we will be talking in terms of say my stator, I will be having secondary losses, I will be having profile loss, I will be having tip leakage loss if it is present. And this is the amount of work, say around 80% we will be getting. So, we can say our efficiency for axial flow compressor, that will be in the range of 80 to 85%. Now, over the year people they have their expertise in terms of design. Now, we are having compressors, they are having efficiency in the range of 88%, 89%. Now, this is what we will be discussing in details, various losses, because that is what is creating trouble what we are talking in terms of flow unsteadiness. Okay. Once you understand these fundamentals, it will give you very good understanding in terms of say unsteadiness, that is what is being caused in my compressor. It says like end wall losses, profile losses, tip clearance loss, secondary loss, shock loss, and what we say is shock boundary layer interaction. Now, when we are talking in terms of say boundary layer, we know we are working under adverse pressure gradient. So, my flow will not be having that energy to sustain or stay along with my blade surface. After some point, it will lose the momentum and you will be having the separation of the flow. Similarly, what we are talking in terms of solid body, what is having, we will be having say growth of boundary layer. So, this is what is creating trouble in terms of my flow physics. Later on, this boundary layer loss, that is what will be merging with my other losses, and that is what is creating more trouble. Okay. Suppose say if I consider you have idea about the cambered one. When I say I am having my angle, that is what is a constraint. I say my delta beta, that is what is my blade turning angle. Blade turning angle, that is what is in the range of say 30 to 40, 45. If it is larger than that, then you have chances for your flow separation. So, if you look at here, this is what is representing my low cambered aerofoil and this is what is representing my high cambered aerofoil. So, if you look at, if I will be having high cambered aerofoil, then I will be having say thicker aerofoil. Okay. Then it will subjected to higher losses. So, if you look at here in this particular region, we will be having thicker wake, that is what is coming out. If I am talking in terms of low cambered aerofoil and say thin aerofoil, so you will be having lower losses, but at the same time the working capacity or pressurizing capacity, that is what is lower. Okay. So, this is what is again depending on so many parameters, what we say in terms of flow parameters, say my Reynolds number, Mach number, longitudinal curvature of my blade, inflow turbulence, free stream unsteadiness, then unsteady boundary layer, pressure gradient, shock strain, so many flow parameters, that is what is changing my flow behavior over the suction surface. Similarly, if we look in terms of say blade parameters, then my thickness, camber, solidity, sweep, skewness of the blade and blade roughness, these are the parameters which are changing my losses or my flow behavior on the surface. Now, earlier days, in order to make those rotors and stators, people they were doing their experiments on say Cascade. So, based on the performance of Cascade, they are deciding how exactly your profile need to be and how exactly your flow angle need to be varied. Okay. So, in order to carry out this is what is known as a linear cascade, in which my flow that will be entering here, it is getting diffused, then after we are having say honeycomb section, then it will be followed by say turbulent screens, then it is getting accelerated as per my mass flow rate requirement or velocity requirement, and that is what is flowing through my flow passage. Okay. So, here in this case, now we need to understand the effect of say incidence angle. Very soon we will be defining that parameter. this particular drawing, if you look at, or the photograph if you look at, this is what is for transonic aerofoil testing. Similarly, here if you look at, this is what is my annular cascade. So, linear cascade and annular cascade, if you look at, if you want to define this annular cascade, that is what is taking care of my variation in along my radial direction. Here in case of say stationary cascade, it is not. We will discuss in detail when we will be talking for turbine. Okay. The logic for turbomachinery and cascade tunnel, that is what is coming nearly same. Now, here if you look at, this is what is representing in terms of my CL for the aerofoil, that is what is my conventional aerofoil diagram, and here this is what is representing my say drag curve or drag bucket. Okay. So, if we look at for my primary loss calculation, like what is the effect of angle, solidity, operating condition, that you can study with the help of cascade. Now, the situation is what we are talking in terms of mixing losses. The name itself says like it is because of mixing of my wake flow with downstream or freestream flow. That is what is happening between the gap of rotor and stator. That means whole my physics, that is what is depending on what need to be the axial gap between rotor and stator. Let me explain here what will happen. Suppose if I will be putting my axial spacing to be larger, my size of the stage or overall stage length of my compressor, that will be increasing. Now, when I am decreasing my axial spacing, then I can reduce the size or the length of my compressor stage. But what is happening now, because since we are having less spacing between say rotor and stator, so your flow unsteadiness or flow three dimensionality, that will be greater in that particular region, and that will lead to losses, that will lead to unsteadiness in the flow. Okay. So, Professor Watanabe, he will be discussing in that aspect. Suppose if I am talking in terms of my axial spacing to be large, we have certain assumptions when we are designing. What is our assumption? It says my absolute velocity, that is what is coming out from the rotor, and absolute velocity, that is what is entering my stator, that is what we are assuming to be constant. When I am increasing that logic is not applicable. So, we need to play with the change of axial spacing. Now, let us talk in terms of tip clearance flow. If we look at tip clearance, as we have discussed, it is a mechanical requirement. So, it says my 30% of loss, that is what is happening in the compressor, is only because of tip leakage loss. And this tip leakage we have seen, that is what is mixing with my incoming flow or the primary flow, and that is what is generating the vortex. That is what is known as tip leakage vortex. We will see in the details. Now, this vortex, that is what is moving towards the stator. That means it is changing the performance of my stator. Now, what are the reasons why we are having the tip clearance? It says my tip clearance we are providing intentionally because we would like to have the rotation of wheel. My tip clearance, that is what is changing with the operation. How it is changing? Because if you look at, we are having the blade, that is what is acting at high pressure. That means it is subjected to say expansion because of temperature rise. So, that is the reason why my gap between stator and rotor, that is what is changing. Okay. Now, the situation is, if we are talking in terms of when it is working under off design condition, I will be having more interaction with thick boundary layer condition, and that is what is changing my performance. Now, let us try to understand this situation. Here, this is what is my incoming flow, that is what is entering. Now, if we look at, we will be having my flow, that is what is moving from my pressure side to suction side. What it will do when it is moving from pressure side to suction side, that is what is deflecting my main flow. That means, this particular region, if you look at, there is a region where we are having low velocity region or flow deficit region. Okay. That is what is acting like my flow blockage. Now here if you look at this particular region, that is what is acting like a flow blockage. In that particular region we have seen our axial velocity seems to be lower. Now what is happening? The interaction between your stator and rotor near the tip region, because of this flow blockage, my flow what need to go towards my stator, it will not go. That means my stator here, it will be working under off design condition. Okay. Or I need to design my stator in such a way that it will take care of this. Okay. Now here this is what is been defined by Professor Tan from MIT. What they say is now how my tip leakage flow, that is what is behaving. If you look at, we have discussed there is a flow, that is what is moving from pressure side to suction side, and that is what is merging with my incoming flow, and that is what is crossing through this passage, and that it will be striking on my pressure surface of next coming blade. Okay. Similarly, what has been observed, like there are with change of my mass flow rate, the situation arises in which my flow that is not jumping from this pressure side to suction side and will strike on my next coming blade, rather it will be moving from the frontal side, and that is what is getting strike on my pressure surface. So it is like this. This is what is my situation, this is what is my other situation. So we can understand the particular part, what we say in terms of tip leakage flow, that is what is very complex flow. And the thing is, your flow behavior in the tip region, that is what is depending on what gap you are providing. You say, sir, provide less gap, tip gap, that is what we will be doing. Okay, no problem. Once your engine or your compressor, that is what is starting, immediately after few runs, your engine will get damaged. The reason is because of your expansion of that blade. There are so many reasons, and that's the reason why, to be on safe side, people they are putting slightly larger tip clearance. Now the situation is, when we are talking in terms of larger tip clearance, my efficiency will be low. Efficiency in the terms what we are talking, that's what is in terms of specific fuel consumption. Now suppose say if we are making compressor for commercial engine, that's what is having say efficiency in the range of 82% or 80%. And your competitor, they claim say they are having efficiency in the range of 89%. It is but obvious the choice will be towards the higher side, and that is the reason why this is what is a particular interest of area where lot of research and development activity, that is what is going on. Recent day people they are talking in terms of tip insensitive rotors, in which they are designing the rotor in such a way that there is no effect of tip clearance. That is what is the art, state of the art, and that is what is a proprietary thing for those engine manufacturing companies. So it will not be available in open literature. Now in overall, let us try to understand, suppose what we are talking of. Now I am having my flow, that is what is entering like this. What is happening? Here I am having solid surface. Okay. Now because of solid surface, I will be having growth of boundary layer along my pressure side as well as on my suction side. When my flow, that is what is striking here near the leading gauge, I am having my adverse pressure gradient. Okay. I am having my radial pressure gradient, because along the radius my pressure, that is what is changing. Then after, what is happening? I am having growth of my boundary layer. All together, that is what is generating the vortex, what we say suction surface or corner surface vortex. Similarly here, I will be having my flow, that is what is moving from my pressure side to suction side. I will be having my incoming flow, that is what is merging together, and that is what is creating tip leakage vortex. Now along the span, we will see very soon, we will be having, because of differential pressure and solid surface, growth of boundary layer, we will be having passage vortex, that is what is happening, that is what is coming out from my rotor. Okay. This is what is in terms of say inflow distortion, we will be discussing when I will be discussing in terms of say flow instabilities. Now, this is what I was talking to you in terms of say changing of your tip clearance. This is what is my design condition. I am having certain amount of tip clearance. Now, because of some reason or because of my manufacturing difficulty or because of my tolerance free rotor design or say fabrication error, what will happen in particular region or some of the blade that will be having axial movement like this. What it will do? It will touch my casing. Similarly, maybe because of my manufacturing error or maybe because of my movement, I will be having the gap to be increasing. Now, when we are talking in terms of say flow instability, when we are talking in terms of flutter, when we are talking in terms of unsteadiness, this is what is playing important role. You will be having catastrophic failure of your whole compressor, or maybe it will be the complete damage to your engine. Okay. So, this is one of the reason why people they are talking in terms of having thorough understanding of flow physics. Now, this is what we are talking in terms of secondary flow. As I discussed, suppose say I am looking from my trailing edge side. This is what is my pressure side and suction side. We will be having the jump of my flow from pressure side to suction side. Similarly, here in this particular region, I will be having 3 solid boundary. What are the boundaries? I will be having boundary near the hub and blade. I will be having boundary along the hub. I will be having boundary near the casing. I am having say solid boundary of the blade. Because of that, you will be having differential pressure, that is what is generating. Along with that, you are having centrifugal action also. That is what is generating my differential pressure in the flow passage. And because of this differential pressure, you will be having your flow circulation, that is what is happening. And that is what is known as passage vortex. Okay. People they are defining that as a secondary flow. And this secondary flow, when we are talking in terms of stator rotor interaction, it is making my whole flow physics very complex. Okay. This is what is based on my different designs. People say 50% reaction design, in which you can be having 2 such kind of vortices. Now, let us move towards the Mach number and the shock losses. What we have understood in terms, my static pressure rise in the compressor, that will be increasing with increase in Mach number. Okay. My pressure gradient, that will be increasing with the Mach number. Similarly, we will be having momentum thickness, that is what is growing with the Mach number. Let us try to understand. Suppose say this is what is my flow between my flow passage between 2 blades. So, if you look at this is what is my performance map at different points. Say this end, that is what is my design point, A point, that is what is my stall point, I will discuss very soon, B and C point, that is what is my operating points. So, if you look at here, now when I am talking in terms of point A, what is my point A? That is what is my stall point. Now, let us try to understand. Earlier days when people they were doing design during 60s and 70s, they found with increasing of rotational speed, my flow that is what was becoming transonic. And that is the reason why they say avoid that kind of situation. Slowly people they have understood, rather taking that as a loss, let us try to understand in other way. Suppose if I am talking here, this is what is my shock that will be attached to my blade, and other end of my shock that will be striking on my say suction surface of my next coming blade. That is what is acting like a normal shock. The property for my normal shock is to give the pressure rise. What is the purpose of our compressor? We need to have the rise of pressure, and that is what we are doing using this kind of aerofoils. So, slowly people they have realized the benefit in terms of having say transonic flow or supersonic flow, and accordingly they have modified their aerofoil. So, if you look at here in terms of aerofoil, that is what is not what conventional aerofoils what we are talking of. They are of some special shape. Suppose if I am talking in terms of say point N, the shock that's what is moving downside. Okay. Similarly, if I am talking in terms of B, that's what is moving downside. And so the thing is, maximum pressure rise, maximum diffusion you are getting when you are at point A, and that's what is this situation. So you are taking the benefit of your normal shock. Now the thing is, this is what we have discussed in terms of three dimensionality. Now here let me discuss in terms of your inlet shock, that's what is entering inside my flow. Now what is our understanding? That shock that will be acting like a blockage of my flow. Okay. And downside of my shock, I will be having steep pressure rise. Now when I will be having very high pressure rise, and that too my passage is diverging passage, then there are more chances for my flow to get separated. Okay. So in terms when we are talking for say turbomachinery, the most complex fluid flow, that's what is encountered. Okay. What are they? They are basically secondary flow because of viscous effect and complex geometry, which is dominated by passage vortex, corner vortex, trailing vortex, horseshoe vortex, sweeping vortex, etc. The inherent unsteadiness, that's what is because of relative motion between your rotor and stator. Now the situation is flow pattern near the wall region, we will be discussing soon. That's what is in terms of laminar flow, turbulent flow and transition flow. Maybe your flow will be subsonic, maybe supersonic, maybe transonic, and due to the limitation of the space, when we are talking say, if we are talking in terms of say military engines, for military engines space and weight both are my constraints. So I cannot put larger space between rotor and stator. There you will be having very small gap between rotor and stator. Okay. So that's what is creating whole trouble in terms of my flow unsteadiness. Now let's try to understand in terms of incidence angle. Suppose say this is what is my situation, this is what is my velocity triangle. This is what will create the platform for your next stage. Let's try to understand this is what is my design condition for particular aerofoil. Because of some reason or my requirement of pressure rise is say change, what will happen? Initially my mass flow rate that will be changing. When my mass flow rate is changing, that means my axial velocity is changing. Suppose let's discuss, we are having my axial velocity that is lower than that my design velocity. What will happen? My rotational speed, that's what is say constant. So I will be having my flow that will be coming out from my or maybe entering in my rotor, that will be at some different angle. Similarly, I can have my different condition, my mass flow rate requirement is higher and my rotational speed is constant. I will be having my flow that will be entering in my rotor, that's what is different. Now that's what is defined as increase in incidence and decrease in say incidence. Similarly, now what is happening? Because of change of my axial velocity, my flow behavior at the exit that will be changing. Now how it will be changing? This particular thing, that's what is under design condition. Now because of change of mass flow rate, because of change of axial velocity, my flow that will not be coming out at my angle beta 2, it will be coming out at some different angle. Similarly, when we are talking in terms of my axial flow to be higher or axial velocity to be higher, I will be having different configuration. Now this is what is representing in good way. What it says, this is what is my stall condition, means stall condition in the sense we will be having my drag to be large. Okay. Now let's try to understand in other sense, as we have discussed the CP distribution, that's what is very important for us. Say this is what is my design incidence condition. I will be having my distribution of pressure or distribution of Mach number. Here it is defined in terms of Mach number. upper surface, that is what is representing my suction surface, lower surface, that is what is representing my pressure surface. Now what happened? Suppose say I will be having my incidence angle, that is what is greater than that of my 0 or my say design condition. Here if you look at, I will be having all the way very high acceleration of flow and then after deceleration of flow. At the same time on my pressure surface, I will be having small acceleration of flow and my deceleration of flow. So if you compare the Cp here, it is clear that we will be getting higher Cp. Okay. Now suppose if we consider in terms of other sense, say we will be having our incidence angle, that is what is less than 0, then what is happening? I will be having my crossing of flow. That means I will be having my acceleration of flow both on suction side as well as on pressure side. This in terms decreasing my pressurizing capacity. Okay. Now this is what is representing. So conventionally people they have understood, suppose that this is what is my 0 incidence line, then on pressure side when we are incorporating or the flow is giving, that angle they are defining as positive incidence angle. Now on suction side then it is defined as a negative incidence angle. Here this is what is for say NACA 65 and C4 aerofoil, what is the change of incidence. So if you look at this center, that is what is representing my 0 incidence case. When I will be having positive incidence case, my acceleration of flow on my pressure surface, that what will be lower. Suppose say if I am talking in terms of negative incidence, I will be having more acceleration of flow. So basically the good design understanding or a good understanding of aerofoil, specially applicable to say axial flow compressor, is how you are managing your flow on the aerofoil. Once you are understanding thoroughly how you are managing your flow, your work, 60% work, that is what is done. Okay. So the thing is, like when people they are using this computational fluid dynamics or any numerical method, what basically they are understanding is in terms of understanding particularly how my flow, that is what is behaving on my pressure surface and suction surface, how my flow acceleration and deceleration, that is what is happening on my pressure surface and the suction surface. Now here if you look at, this is what is the configuration with different thickness. So this situation if you look at my maximum thickness point, that is what is say different, then my Cp distribution that will be changing. So the thing is, only aerofoil, that understanding with incidence will not help. You need to understand how my thickness distribution is provided on my blade. That is also very important. For both the cases, when I am changing my say inlet Mach number to be larger, I will be having my larger Cp. So this is what we have discussed. Now the question will come like, sir, how do we decide the number of blades? So conventionally over the year, what people they have defined is you need to have even number of stator and prime number of rotor. That is what was the logic, and if you open your old engines, that is what is having this kind of configuration. Now the situation is, people they have understood the importance of selection of number of blades. So if you look at your high bypass ratio fans, for those high bypass ratio fans, they are selecting even number of blades. The reason is, say it is easy to replace your blade, at the same time what balancing efforts you need to put, that also will be reducing. Okay. Now the situation is, what flow unsteadiness what we are talking of, that is happening even by the selection of this number of blades. So that is also one of the criteria or one of the reason why the number of selection of blade, that is what is very important when we are talking in terms of flow unsteadiness. Now let us talk in terms of one more angle, that is what we define is in terms of my deviation angle. What is happening at the inlet, what angle we have defined, we are defining that as an incidence angle. At the outlet, we are defining that as a deviation angle. So the thing is, what is happening, because of adverse pressure gradient, across your aerofoil inlet and outlet, the flow that will get separated, or you will be having low momentum fluid both from suction side and pressure side, that will be coming out. And when it is coming out, it will be acting like a negative jet. So, the thing is, when you are doing design, purposefully designers, they are accommodating that deviation angle in the calculation, so that like this kind of situation what we say will not occur, or it will take care of the flow separation situation. This deviation angle, that is what has been calculated by the rule, that is what people say as a Carter rule. Nowadays with numerical tools, computational tools, people they are moving with say CFD analysis, and based on that, based on the flow physics across the surface, they are deciding the deviation angle. Okay. One more angle, that is what we have defined, is a say stagger angle. That stagger angle, it is with axial direction and the chord. This is what is known as say my stagger angle. Now, this stagger angle, if you try to understand, this is what is my normal operating condition. Now, what I will do, I will stagger, or I will increase this angle or decrease this angle. Suppose say I am decreasing this angle, what will happen? I will be having my flow turning, that is what will lead to the flow separation. Okay. Suppose say if I am increasing my stagger angle, what will happen? I will be having my separation of flow, that is what is happening on my suction surface, and that is the reason why I will not achieve what diffusion I am expecting. So, that is the reason why in order to accommodate the mass flow rate, or in order to control the mass flow rate, that is what is flowing through the passage, that is controlled by the staggered angle. Now, what we say is in terms of my maximum camber. So, if you look at the distance A, that is what is known as location for my maximum camber. Here if you look at, we are having say circular arc camber line. So, this is what is my CP distribution for that. If we look at, if I am shifting my maximum camber towards the leading edge, then my CP distribution, that is what is changing. That is what is known as say aft loaded kind of blade. Here if I am changing my maximum camber towards say my rear side or trailing edge side, that is what is known as 4 kind of loading. So, you can clearly visualize this loading. Now, the thing is, there are different kinds of camber lines people they have defined, say circular camber line, parabolic camber line, polynomial camber line, exponential camber line, multiple circular arc, double circular arc. So, as per the requirement, as per the design requirement, people they are adopting the circular lines. So, mainly this circular and parabolic, that is what people they are using for subsonic compressor design. When we are talking in terms of say transonic, then we are using say polynomial, exponential, or double circular arc or multiple circular arc. Okay. Now, when we are talking in terms of say transonic rotor, let us try to understand why exactly we need to understand the transonic rotor. What we have observed, like my radius, that is what is changing from hub to tip region. Now, what is happening with change in my radius, my peripheral speed, that is what is changing. When my peripheral speed is changing, my relative velocity with which my flow is entering, that is what is changing. That means my relative Mach number, that is what is increasing. Okay. So, what will happen? Near the hub, you will be having low relative velocity, near the tip, you will be having high relative velocity. So, we can say near the hub, let me show you, this is what is. So, half the blade that will be acting in subsonic region, near this tip region, it will be acting like supersonic region. Okay. Now, as we have discussed, what is happening on supersonic or transonic region is, this is what is my bow shock, that is what is entering inside my compressor. Now, since this is what is having the curvature, that is why it is subjected to say expansion waves. These expansion waves that will increasing my velocity, At the same time, what is happening, the other end of my bow shock that will be striking on my suction surface. This will act like nearly normal shock, and that is what is giving me rise of pressure. So, upstream of my normal shock I will be having low pressure, downstream of my say normal shock I will be having high pressure, and within this passage I will be having very high pressure, and outlet pressure what I am expecting that to be large. Okay. So, now the situation is, in order to have my shock to be placed properly, I need to accommodate that shock, I need to have attached shock. Suppose say it is a detached shock, then that is what is subjected to loss. I need to place my blade leading edge in such a way that I will be having always attached shock. So, that is the reason why if you look at the leading edge, suppose say if we talk in terms of this blade, what is happening? Say this is what is my leading edge region, this leading edge, that is what is say having very less thickness, and that is what is sharp. Now, in terms of supersonic and subsonic, as I have discussed, there are different configurations which are possible, and the situation is, as we are moving towards per pressurized requirement increasing, nowadays almost all your rotors, what we are talking in terms, your LP rotors, they are of transonic nature. Let us try to understand in terms of transonic definition. What we say is in terms of my Mach number. That Mach number that will decide whether my flow is subsonic, transonic or supersonic. What is happening with moving towards downside or the rear stages, my temperature that is what is increasing. So, when my temperature that is what is increasing, my Mach number that will not be transonic, that will be lower. So, the thing is, in your HP compressor you will be having your flow high subsonic. Okay. So, for the front stages, if we say like for fan or what we are talking in terms of LP compressor, most of the stages they are having this kind of blading, what we say transonic blading. Suppose say if I am talking in terms of say HP compressor, here if you look at that is what is having the shape similar to what we have observed for subsonic aerofoils. So, this is what is the rotor or the rotor segment for HP compressor. Okay. Now, these are some of the configuration. You can read in detail how we are managing our flow. Now, this is what I was talking to you in terms of my expansion waves and normal shock. Here, if you look at, it is dedicatedly been defined. Here I am having supersonic diffusion, that is what is happening, and downside I will be having subsonic diffusion. People they have defined different way. They say shock in rotor, that is what is having shock to be placed. My whole stator that will be subsonic. Some design they say they will be having supersonic say shock in rotor as well as shock in stator. Suppose say I am talking specially for the application, say when we are talking for the application of space engines, where the space is main constraint. We want that engine to be small, one thing. Secondly, the operation time for that engine is also very small. So, the thing is it will run for 2 minutes or 3 minutes and that is it. So, that is the reason why for that kind of configuration, that kind of compressor design, this is what is more preferred. Then we will be having shock in rotor, shock in stator, and these are the aerofoils what we were discussing. This is what is. So, if you want to have more detail, I have given that material in which I have discussed in detail about say all kind of aerofoils. Now, there are different philosophies, say main engine manufacturing companies, if we focus, say this is what is the philosophy for Rolls-Royce engines. Earlier engines, if you look at here carefully, what is observed, like the blades are taller blades, and those taller blades they are having problem with the flutter. Okay. In order to provide the sufficient strain, they have done lancing here. Now, when we are doing lancing, basically we are obstructing our flow, and when we are obstructing our flow, that will deteriorate the performance. Over the year, people they have done a lot of research and development activities. So nowadays they are having special 3D shape blades. If you look at, this is what is 3D shape blade, and this is what is say with alloys they have made. So if you look at, this is what is alloy blades. Similarly, we are having philosophy by GE. Earlier engines they were having same approach. Now the thing is, as we have seen, my thrust requirement for the aircraft, that's what is increasing, and we are looking for say high efficient engine. So most of the thrust we are generating using our say fan. Okay. So the diameter of the fan, that will be increasing. So if we look at overall length or the height what we are talking, that's what is increasing. Suppose if I consider for this engine, particular engine, that's what is having casing diameter of 2 meter. Okay. And the blade height, that will be roughly say 800-700 mm. Okay. So the thing is, there you will be having more trouble in terms of what we say as a flutter. Okay. Now remaining portion after tea break we will be starting with. Okay. If you are having any query, you can ask till now. Next session we will be discussing more in terms of operation of compressor. That's what is flow instability in axial flow compressor. Yeah. So now coming to the next session, like whatever we have discussed up till now, that's what is talking in terms of fundamentals for say axial flow compressor. Now let's move with the performance characteristics. That's what is very important, and slowly we will be moving towards the performance instability what we will be observing in axial flow compressor. So if you look at here, this is what is representing the single stage axial flow compressor characteristic. Now this curve, what we say, like I have my design point, this is what is my design point. Say that design point I am representing in terms of phi as well as psi. So this is what is non-dimensional speed what we are talking, and non-dimensional pressure rise. So this point N, that's what is my design condition. You can have look at, this is what is my solid line, that's what is representing my velocity triangle. Now what is happening, suppose if I say I want to have more pressure rise. So I want to move from point N to point A. What I need to do is I need to decrease my mass flow rate. Now this decrease in mass flow rate, that's what is represented by decrease in my axial velocity. So here if you look at this point, what we say as dash line, that's what is representing my low axial velocity. Okay. Now when I am moving towards say low pressure rise requirement or say high mass flow rate side, my axial velocity, that's what is changing. Now this point A and B, that's what is not arbitrarily been done. The thing is, this is what is based on my overall system. So you might have studied something, that's what is known as say losses in pipe. For that you are calculating different kind of losses, that's what is happening in all my components. So if I will be putting my throttle curve or say my curve, that's what is representing my system, then it will be starting like this, and that's what is meeting my mass flow rate and pressure requirement. Similarly this line, similarly this line. We will see what exactly is that. Okay. Now the situation is, here in this case, if you look at, we are having two different kind of performance map. So this performance map, if you look at, that's what is having say flatter characteristics, and here if you look at, this is what is having steeper characteristic. So now you need to understand, suppose if I am getting my performance map like this, that means this is what is representing my low speed axial flow compressor performance map. Now here if you look at, this is what is steeper, That means that's what is representing my high speed performance map. It is not like say like looking to that. The thing is what we know in terms of our incidence, that's what is playing important role. What is our observation? For low speed we will be having thicker leading edge. That means I can have very good control of my flow over the leading edge. So, on this particular we will be having very good control of my flow. So, my flow is incidenting say on pressure side or suction side, accordingly I will be having my performance map. When I am talking in terms of say transonic aerofoil, what is happening? I am having very thin leading edge. Now, when I am having very thin leading edge, what will happen? My range for incidence angle is low. That means I will be having very steep pressure rise. Okay. So, this angle or my flow, that is what is very sensitive to my leading edge shape. Okay. That is how we are having this kind of configurations. Now, if you try to understand what we say in terms of incidence angle, slowly we are moving towards what is our expectation for understanding the instability. Suppose say if I consider this is what is my positive incidence. What I mean by positive incidence? I will be having my flow towards my pressure side. So, I will be having my separation of flow, that is what is happening on my suction side. Suppose if I will be having my incidence angle to be negative, then my stagnation point, that is what is moving towards my suction surface, I will be having my separation flow from the pressure side. So, it is not the case the separation happens only on my suction surface, separation may happen on my pressure side also. Now, this is what is my performance map, that is what is been represented in terms of non-dimensional mass flow rate and non-dimensional pressure rise. So, if you look at here this point 3 as I have discussed, similar to that, this is what is my design point. Here I have my point 2, that is what is my maximum pressure point, and below that if you look at my pressure is not getting rise, it is falling. So, this particular region, that is what people they are defining as surge limit. We will define this surge very soon. Okay. Now, what is happening? Suppose if I am talking in terms of moving towards say high pressure side or moving towards say low mass flow rate side, the phenomenon what we have discussed is in change in terms of change of my axial velocity. Now, what is happening? Since my axial velocity that is what is reducing, what will happen? If you look at here, these are the blades I have open in one plane. Now, when we are opening in one plane, my flow that will be incidenting here at say blade A. If you look at, that is not incidenting at what we have designed for. So, it is other than my design situation. What situation? What we say is in terms of I will be having say if you move back say here, this is what is my positive incidence kind of thing. So, here because of this incidence change, I will be having my flow separation to be occur. Now, what will happen? Because of my flow separation, my flow will get deflected. That will increase my angle of attack, what we say in terms of change of incidence. Now, my blade that is what is moving from my suction side towards the pressure side. So, after some time my blade A, when it will be reaching to position C, I will be having that is acting in say my design condition. So, here you will be having this flow separation that will be moving in the direction opposite to the direction of the rotor. Okay. That is what is lead to change in terms of my pressure distribution on the blade. When I say change in pressure distribution, you need to understand my blade is getting loaded and unloaded. What you mean by loaded and unloaded? It will generate the pressure rise as per my requirement and it will not generate the pressure rise as per my requirement or what it is been designed for. Under that condition, my blade will subjected to catastrophic failure. So, this what Professor Watanabe will be discussing in his lectures. Now, for multi-stage axial flow compressor, suppose if I say I am designing my engine here in India, suppose a person who is designing the engine say abroad, maybe say in Europe or maybe Russia. So their operating temperature, that's what is different, their operating pressure is different. Here if we are talking, here we will be having operating temperature and pressure, that what will be different. So the situation is, suppose say someone is supplying that performance map what we are talking of, that's what is based on their performance what they have observed in Russia. And if the same engine, if we will be testing here, I will say I will be having hot environment, that is the reason why my engine is not giving that pressure rise. So it is not the case. You cannot say this is what has been designed in particular region, that is the reason why engine is like not performing. To avoid that kind of situation, people they have defined their standard temperature and pressure condition. So if you look at here, the performance map what is defined is given in that sense. It says by normalized mass flow rate and normalized pressure ratio or pressure ratio. So now before going into the details, let us try to understand, say this is what is the performance of individual stage. If we look at here, this is what is for multi-stage axial flow compressor for the engine. Okay. Now for this engine, they have done performance mapping for first stage, stage 4 and stage 7. When my compressor, that's what is rotating at the low speed region. Now what is happening, since it is rotating at the low speed, so you will be having my first stage, since it is rotating at the low speed, I will be having my density to be lower. And because my density to be lower, my performance point, that's what is coming here. This is what is in the region of stall. If I am talking in terms of say stage 4, that's what is near to my that region. But at the same time, for the last stage, if you look at my point, that's what is moving towards say safer region side or maybe on the other side. Okay. So for the same compressor, if you look at stage 1, that's what is performing differently, my stage 4, that's what is performing differently, my stage 7, that's what is performing differently. What is the reason? That's what is because of your change of density. Now in the later stage, what is happening? We are having the rise of density, and that's what has been taken care in terms of my axial velocity, because I am having same point what we are plotting in terms of mass flow rate. Suppose say if I am talking in terms of say mid speed region, what is happening? My almost all points, that's what is near to the stall point. Okay. And suppose say if I am rotating the compressor at the high speed, what will happen? Because of higher rotational speed, my first stage density that will be larger, and that's the reason why it is moving towards my right hand side. Okay. Same way my stage 4, that's what is nearly stall region, and if we look at for stage 7, what is happening? That's what is moving on the left side. So if we look at in overall sense, suppose say when I am rotating my engine at the lower speed, there are more chances for my stage 1 to get stall. When I am rotating my compressor at high speed, my last stage is having more chances towards the stall. Okay. Let's try to understand in terms of overall map. So here if you look at, this is what is representing my surge line. We will see what is that. Here in this case, this is what is the situation, what we say, it is having steep curve. The situation is when I am talking for the low speed region, say this is what is the safe operating range. So for all aircraft, they are defined with this safe operating range. So pilots, they are also aware of this map what we are talking of. Suppose if I am talking in terms of say other situation, say this is what is a line, that's what is representing my choking line. So at the low speed, as we have seen, my density, that's what is changing, and that's the reason why my area, that's what is changing, and that's what is subjected to having the choking condition. Now when I am moving towards the high speed region, what is happening? My inlet, that will get the choke, and that's the reason why I am having this vertical line. Let's try to enlarge that in other sense. Suppose say we are having point A, that's what is my operating point. Now I want to increase my pressure. So what I will do, like I will be decreasing my mass flow rate, and that's what is moving towards B. Now since this is what is high speed condition, you are moving more towards the stall region. What is getting stalled? It says my last stage that will subject it to stall. Okay. Suppose say if I am operating at the point C, what it means, I am operating at the low speed. When I am operating at the low speed, what is happening? I am having my first stage that is subjected to stall. So this is what is representing the situation. And if even if I am decreasing my speed, there will be having a kink kind of situation. Okay. Now here let's try to understand what exactly is happening. Suppose say this is what is representing my velocity triangle. As I told, velocity triangle, that's understanding is very much important when we are talking in terms of turbomachinery. Suppose say this is what is my axial velocity for my point A. Now what is happening, since my mass flow rate we are reducing, so my axial velocity will be reducing. So this is what is my axial velocity reduce. What it will give me? It says that will increase my incidence angle. Okay. When I am having increase of my incidence angle, what we have observed? We are having my flow to get separated in that region. Okay. Similarly, suppose say if I am talking in terms of point C, what is happening? At point C, my speed is lower. Okay. So this is what is representing my first stage. What it will do, since my mass flow rate that's what is lower, it will be having positive incidence angle. Suppose if I am talking in terms of say last stage, what is happening? That's what is acting under negative incidence angle. Okay. So this is what is giving more prone towards my stalling of stage 1. Okay. Now the situation is, what people they are talking of having some kind of solution. What solution they are talking of? If you look at here, what is my operating requirement? I want to have my front stage that to be rotated at low speed, and I can rotate my later stage at the high speed. That's what is giving idea towards the development of multi-spool configuration. So the problem what we are getting in terms of say my front stage stall or the rear stage stall, that can be avoided, or maybe we can increase our limit by providing the multi-spool configuration. Now let's talk in terms of say instability in terms of my compressor. Now this compressor what we are talking of, that's what is this body, that's what is aerodynamic body, that's having its own performance. But it is not the only case, my upstream condition and downstream condition also is having effect on my performance of the compressor. So let's try to understand here. So we will be having two types of the stabilities, that's what is happening. One we say is in terms of say operational stability, and second what we say is in terms of say aerodynamic stability. The operational stability, as I told, like it is a matching of performance characteristic of compressor with downstream component. So you need to have matching of your component, like compressor that will be matched with the combustor, that will be matched with your turbine, that will be matched with your nozzle. That's what is the requirement. When we are talking in terms of say aerodynamic stability, that's what is because of say steady state operation in terms of say stall and surge. Okay. Let's try to understand. Suppose when we are talking in terms, so operational stability, as I discussed, that's what is depending on my inlet ducting, guide vanes, rotor, stator, any pressure recovery device, that's what is creating my whole system. So it is in terms of say whole system performance. So here if you look at, as I told, this particular dotted line, that's what is known as total operating line. Okay. Because of time constraint, we will not be discussing. Those who are interested, maybe we can discuss in detail at that point. So here if you look at, if I will be putting my slope, that slope is coming negative slope. What it says, when it is operating under negative slope of pressure rise, it says it's a stable operating or stable operation. Now let me move towards the other side. Suppose this is what is my situation. What will happen? That's what is operating on positive slope region. That's what is defined as, say, unstable operation. Okay, or my stage is getting stalled. Here this is what is having slope to be higher, but rarely this kind of situation, that's what is happening for the compressor. Now let us try to understand the operational stability. Okay, so here, as I told, this is what is my throttle line for point A, throttle line point B, throttle line for point C. What is happening? This is where I am having, say, negative slope, that means it's a stable operating range. Here somewhere I will be having, say, negative slope, positive slope, that's what is giving me unstable operation. So here my input energy, that's what is higher than that of my losses, and that's the reason why my system is working fine. In this region, my losses, that will be higher than that of my input energy, and this is what is representing my maximum efficiency point. Now let us try to understand the stall mechanism. That's what has been defined in two ways. It says individual blade stall and rotating stall. When we are talking in terms of, say, individual blade stall, that's what is mainly been observed when we are talking in terms of, say, linear cascade. Okay. When we are talking in terms of, say, rotating stall, that's what is happening in my rotor. Okay. So with the interest of time, let us try to understand what exactly is happening. Slowly we will be moving towards one more phenomenon, what I have discussed as a surge. Say, the thing we are defining two instability, that's what is happening in the compressor. One, it is defined as, say, rotating stall, and second, that's what is known as, say, surge. So rotating stall, it says non-axisymmetric, and that's what is aperiodic. When we are talking in terms of, say, surge, it is axisymmetric and periodic. We will discuss this in detail. Now the situation is, what is happening? Suppose, say, this is what is my situation. What we have observed, suppose this is what is my blade, I have open in one plane. Now for this region, this blade phi, that's what is operating in a safe region, or say that's what is as per the design. Because of some disturbance in the flow, that disturbance in the flow may be in terms of, say, inflow distortion, it may be because of your shock present, it may be because of some change in my flow condition, it may be because of my change in the mass flow rate. What will happen? My flow, that's what is not striking exactly at what we have designed for, and I will be having my separation of the flow. Now that separation of flow, what it will do? It is trying to move in opposite direction. We have seen this is what is my direction of rotation, and in opposite direction this is what is moving, and that's the reason why this is what is known as rotating stall. This is what is in line to stall what you have understand in your aerofoil aerodynamics. Okay. Now what will happen? Next stage, my blade that will be passing. So my blade 4 that will be under design condition. Now blade 3 that will be having, say, new stall that will be formed. So here if you look at, you will be having these stall cells that will start making here in that deep region particularly. Okay. And that's what is defining as, say, rotating stall. Okay. Now this stall cell, they have observed it may be more than 9 in numbers, and their rotational speed will be about 50% of your rotational speed of the compressor. Okay. So I will be having my stall cells, that's what is being present here near the tip region. Later stages, what will happen if you will not care for, then the stall cells together that will move forward or move towards the hub side, and that will cover half the region, or that's what is defined as full span stall. In further cases, it may happen whole your annulus that will be covered with your stall cell, and that's what we are defining as surge. Okay. Now let us try to understand here in this case. Suppose, say, if I am talking in terms of say low speed operation, where we are having our front stage, that's what is getting stalled. Under that condition, you will be having this kind of mechanism. So, I will be having stall cells, they are present on the periphery. When I am talking in the mean speed region, then it may be possible you will be having full span stall. When I am talking towards the high speed region, I will be having whole my annulus that will be getting stalled. That is what is defined as surge. Still, we are not defining that surge in that sense. Let us try to understand what we define in terms of say stall. The stall people, they have defined in terms of say progressive stall and abrupt stall. So, if you look at here, this is what is in terms of say progressive way. Okay. Now, here this progressive stall, that is what people they have observed, that is what is happening because of multiple stall cells. So, now you need to understand rotating stall and stall cells. Now, when we are talking in terms of say abrupt or the spike stall, that is what is sudden droop in the pressure, and that is what is very dangerous. Okay. Let us try to understand what exactly and how exactly this progressive stall is happening. Here somewhere, as we have discussed, we are having stall point. Now, even if I am decreasing my mass flow rate, what is happening? Rather increasing my pressure is getting decreased. Why it is? Here if you look at my tip region, that will get stalled. So, you will be having part span stall, that is what is happening. What it will do? That is what will not give permission for my flow to enter as per my requirement. Okay. Further downstream, if you are decreasing your mass flow rate, this is acting like a patch, it is kind of blockage. Okay. Even if you are decreasing, it may possible it will go in the deep stall. Okay. So, now this philosophy, that is what is based on the design of the rotor. Many design what we are observing these days for the engine, they are tip loaded rotors. Tip loaded rotors in the sense the chances for my flow separation to happen near the tip will be more. Okay. So, my initiation of stall, that will be happening from the tip. There are some rotors people they have designed, they are say hub loaded. So, there you will be having your separation or flow separation, that is what is happening near the hub region. Okay. Now, how exactly this is what is happening? So, most of the cases, that is what is subjected to say change in the differential pressure of compressor between the intake and the combustion chamber. Why this compressor is getting stalled? Let us try to understand that part. What it says, when you are doing overspeeding, okay, you need certain amount of time for your flow to get stabilized. Then engine operation outside the specific engineering parameters, that is what has been defined. You cannot have more expectation, you cannot be crazy when you are running your compressor. Turbulence or the disturbance in the flow at the intake. Now, this is what is creating a lot of trouble. In sense, when you are flying in aircraft, there will be announcement saying like it's turbulence, so just put on your belt, and then you really find the sake of whole aircraft. That is what is a critical situation. What it is doing, the air, that is what is entering inside my compressor, it is other than the design condition. So, whole my compressor, that will be working under off design condition. Okay. And that is what is giving you bang and kind of vibrations. Then contaminated or the damaged engine components. Suppose say we are talking in terms of say volcanoes, or maybe there is a high wind of your sand. What will happen? That will get impinge on your rotor blade or maybe stator blade. There it will get deposited, what we say for an object deposition. What exactly it will do? That will change my surface, and once it is changing my surface, whole my flow physics, that is what is happening on my suction surface and pressure surface, that will be changing. So, that is also one of the reason. So, rotating stall, that can be considered as precursor for the surge. Once the rotating stall happens, immediately you will find my engine will get surge. and that's the reason why rotating stall that need to be prevented or the controlled. So people now they are doing their lot of research and development activity to avoid that kind of situation, or say your engine or the pilot will get the idea, now my stage is getting stalled. Okay. So there need to be something like they are identifying the location from where you will be having the precursor or maybe occurrence of this stall that will start. Let me tell you, this rotating stall, it is not having fixed location from where it will start. It depends on so many parameters. Okay. Now let's try to understand when we are talking. This is what is the locus of point where you will be having say surge or the stall operation. Here if you look at when you are running your engine at a low speed, the intensity of the disturbance that which is lower. When we are talking, disturbance are severe and that will be abrupt. When we are talking in this sense, you will be having combined effect of compressor and combustion system that will be storing the energy, and that's what is creating the surge. Let's try to understand what surge is. Now here, this is what is a performance map what we have taken from the literature. They have done their experimental work. Now the thing is, in order to understand, people they have understood the stall, they have understood the surge, but not in that detail. So the work, that's what was reported in open literature for the Viper engine, Rolls-Royce. What they have done, they have run their engine by overfueling at different tests. They have conducted 7 tests. Let engine be get damaged, no problem. So at the low speed configuration, say 50%, 55%, if you look at when you are doing your overfueling, you will be having some kind of flow instability. That's what is happening. So this is what is captured by unsteady pressure probes. Okay. So here what I was talking to you is in terms of this disturbance, that's what is of lower intensity. Now when we are talking towards say higher speed or maybe in mid region speed, this is what is the reduction. If we look at here, this is what is the severe situation you are observing. If you look at 83%, you will be having very high pressure fluctuation, that's what is happening. And even if we are moving at the high speed or the near design speed, and that too in the surge limit, then you will be having the surge, that's what will be happening. And that surge, that will be subjected to flame out. Let's try to understand what exactly and how exactly it is happening. Now when we consider here, say I have my system, whole system, what is happening? I will be having my rise of pressure up to certain point. So that rise of pressure, that will be entering inside my combustion chamber. Now when I am doing my throttling or when I am decreasing my mass flow rate, what is happening? Now what pressure, that's what is going inside my compressor, that will be decreasing. So what will happen? I will be having low pressure region on the front side. I am already having high pressure, that's what is present at the inlet of my combustor. So now there is a differential pressure, so my flow that will try to move in reverse direction. So it's a flow reversal sort of thing. Now again what will happen when it is moving downside? Again my pressure, that's what is increasing, downside pressure is say decreasing, again it will try to move. So you will be having forward and backward motion, and that's what will give you flame out, and that's what is the damage of whole your engine. Okay. So the thing is, if you look at here, this is what is been represented in a nice way, saying when I will be having rotating stall, this is what is my frequency, that will be in the range of 50 to 100 hertz. When I am talking in terms of say surge, just try to understand rotating stall, that's what is circumferential phenomena. Okay. When I am talking, and that too is for individual stage. Okay. When I am talking in terms of surge, what is that? Actually, that's what is my axial phenomena. So I will be having backward and forward movement. Okay. So we need to understand rotating stall and the surge. By happening of rotating stall, you will be having surge. Okay. Now, Professor Zitzer, he has defined one parameter. He has defined that in terms of pressure force and the inertia force. What he says, like when you will be having, say, your pressure force that will be dominating, under that condition your compressor will go under surge condition. It says when you will be having your inertia force that will be larger, it says your compressor will go under rotating stall condition. Now the situation is, it is depending on what we are talking in terms of connecting ducts. Suppose say compressor is attached with the short duct, it will get shock or it will get stall. Whereas compressor, that is what is attached with some storage device, say combustion chamber, then it will surge. So when we are conducting our experiments in a laboratory for the testing of this compressor, mainly we are talking in terms of stall. Okay. So we need to understand how exactly surge and stall, that is what is happening. So as we have discussed what is happening, my operating curve, we are moving towards the left. When we are moving towards the left side, then what is happening, my mass flow rate, that will be decreasing, and that is what is decreasing my pressure ratio. Because of differential pressure ratio upstream and downstream, we will be having the reversal of my flow from forward and backward direction. Okay. So this will lead to catastrophic failure, what we have discussed, and you need to shut down your engine. Okay. Now for surge, people they have defined as, say, mild surge, they have defined classical surge, modified surge and deep surge. Let us try to understand. If we are talking in terms of mild surge, that is what is, the thing is, let us move back what we were discussing in terms of performance map here. Now that is the reason we have defined as engine operating line, and this is what is defined as my surge line. So when the pilot is operating the compressor at particular speed, he will always care for, and this is what is defined as surge margin. So for all engines, this surge margin, that is what has been defined. Okay. So when he is moving towards this point, suppose this is what is my operating point, when he is trying to move towards a high pressure expectation, what will happen? He will get idea about the mild surge. Okay. And that is what he will care for, otherwise it will go into deep. Okay. Then classical surge, it says oscillations are larger at low frequency, but the flow reversal will not happen. And the classical surge, it says like mixture of rotating stall, that is what is a classical surge. The entire flow fluctuates in axial direction and it is unsteady and axisymmetric. Then we say deep surge, that is what is complete flow reversal that will be happening, and this is what is highly undesirable phenomenon. So the thing is, people they are defining surge in a different way. What they say, it is a most unfortunate occurrence to befall in aero engine. It's a most serious problem in the aerodynamics of turbomachinery. Someone says like it's a violent phenomenon constraining the operating range for the compressor. It's say like it is something that need to be avoided. Okay. Now let us try to understand what we are talking in terms of flow distortion or flow instability. As I discussed, the thing is there are so many parameters, that is what is affecting my performance of the compressor, that is what is giving you rotating stall. Okay. Now one of the situation is in terms of my inflow distortion. Suppose say this is what is my normal operating condition, as per my design condition my flow is entering, so I have no problem with. Suppose when I am taking off or I am doing landing, what will happen? Some of the region my flow is not entering. Now my flow is not entering, what it means, this region my mass flow rate may be less or maybe 0. That means that particular region I will be having my rotating stall to occur. It may possible very soon it will get surge. Okay. So, the thing is, this is what is my head wing. There may be say tail wing rigid situation, crosswind situation, crosswind with some yaw angle. There are different conditions. This is what we are talking in terms of my flow turbulence, that is what is entering. So, this inflow distortion, that is what is having adverse effect on my stability of the compressor. It may be possible because of this inflow distortion, my compressor will go in surge, sometimes power loss or the flame out also will happen. Now, the question is how exactly this inflow distortion that is occurring. It says when you are doing maneuvers, suppose if I am talking in terms of military aircraft, I cannot have always inline flow. Flow separation in the intake due to the shock and boundary layer interaction. We will be having wake of aircraft or the other aircrafts. We will be having vortices, we will be having crosswind, we will be having atmospheric turbulence. So many causes are possible when you are flying your aircraft, and all this, that is what is creating trouble, what we say in terms of inflow distortion, and that is what is defined as say your instability generating device. Okay. The flow may be entering inside your turbomachinery, may be in radial direction, it may be entering in say circumferential direction, it may be combined, and this inflow distortion may be of different kind. It may be because of pressure, it may be because of temperature, it may be because of velocity. So, when we are talking classically, people they have defined as radial inflow distortion, which is axisymmetric in the nature. When we are talking in terms of circumferential, that means you will be having your blade that is subjected to distortion and it will come out. So, that is what is highly unsteady flow. I will show you what exactly is the meaning. Now, the classical theory, what it says, suppose say this is what is represented in terms of distortion, that is what is defined as say distortion screen. Let me explain. Suppose say you are working in the domain of say aerodynamics. When I am putting my screen, you say I am decreasing my turbulence, I am smoothing my flow. When I am talking in terms of say engine, or when I am talking in terms of compressor, I say this is what is distortion generating device. So, here if you look at, suppose say half of the compressor, that is what is been covered with say distortion screen, half of the compressor or the region, that is what is without distortion flow. So, if we put my operating, it says when I will be having distorted flow, I will be having more pressure rise, but my mass flow rate is lower. Okay. When I am talking in terms of undistorted, most of the mass flow rate, that is what is moving in undistorted region, that is why it is higher mass flow rate, I will be having low pressure. And in overall, if you look at, my performance will be somewhere here. Okay. Now, the situation is when we are talking in terms of say fighter planes, what we say, it need to do a lot of maneuvers, and when it is doing that maneuvers, there may be chances that you will be having flow distortion that will be entering in your compressor. It may subject it to rotating stall, it may subject it to surge, and it is a failure of engine. So, the thing is, people they started doing their design, they are giving something, that is what is known as distortion index. That is what is defined as per say European Indian, they are defining in a different way, Americans they are defining in a different way. Okay. That is what is defined as a DC 60, DC 90. Okay. So, if you look at, when I say DC 60, this is what is my spoiling angle. It may be 22.5, it may be 40, it may be 90. So, this is what I have done at IIT Bombay during my PhD study. So, my whole study that was defined in terms of say what is the effect of distortion on counter rotating fan stage. This counter rotating because of time constraint we will not be discussing in detail, but The whole idea is to represent how the distortion study it has been done. If you look at here, this is what is my distortion screen that's having say 90° sector. I have used 3 different 7-hole probes. One is placed at the entry of my rotor 1, one is placed between the rotors, and one is placed at the exit of my rotor 2. That's what is to capture my total pressure, velocity, flow angle, different parameters. Other study I have extended with radial inflow distortion, that is what is hub region, it is covered with the distortion screen. Tip region, that's what is covered with the distortion screen. Then the combination of say low porosity index and high porosity index, that's what is giving me complex flow physics. So this is what is my experimental setup. Now in order to study what is happening throughout my passage at the inlet, at the exit of my rotor 1, at the exit of rotor 2, my distortion, I kept my probe in same position. My distortion screen I have rotated in the interval of 15°. So this is what is my performance map. So if you look at here, this is what is my design speed condition. This field 1, that's what is representing my clean flow condition. This empty, that's what is representing my say distortion condition. So if you look at here, with increase of speed, my performance, that's what is improving both for clean and distorted flow. But when I am talking in terms of operating range, you can say my operating range is decreasing. When I say operating range means overall range of my operation. After this I cannot operate my setup. What it says, that's what is my stall condition. Okay. Now this is what is my total pressure contours at the inlet, at the exit of rotor 1, at the exit of rotor 2. Since I have kept my distortion screen of 90° sector, what flow physics I am capturing is like this. Here the purpose is not to explain in terms of what is happening. The whole purpose for the study is, if you look at carefully what is happening, though I am giving my distortion at the inlet, at the exit of my rotor 2, I am getting my clean flow. So the thing is, that's what is a requirement. Suppose in case you will be having distortion, that's what is present upstream, downstream you will not be having any distortion. So this kind of logic people they started using. But here you need to understand what is happening. So here if you look at, this is what is my rotational direction of rotor 1. So what is happening? Suppose I have one blade. That one blade, that's what is approaching towards say distortion screen. What will happen? My mass flow rate will be decreasing. So that will be acting at say low incidence angle, or my incidence angle is changed. Now when it is coming out from the distortion, my incidence angle that will be increasing because my mass flow rate is changing. So this is what is been represented in that sense. So here this is what is my design condition. When I will be having higher incidence means my blade coming out from the distortion, under that condition this is what is my velocity triangle. So whole your logic, whole your study, that's what is based on your velocity triangle only. When I am talking, when my blade is approaching distortion, it will be having low incidence angle. So here if you look at what we are talking in terms of diffusion, that's what is different. Then this is what is with hub strong complex distortion, my performance, that's what is further decrease. This is what is my situation when I am talking in terms of my hub region, that's what is having low porosity region. Similarly, this is what is with tip. Now the situation is, as I told, inflow distortion, that's what is creating whole trouble. And when we are talking in terms of the design of engine, during design we are not taking care of this distortion, and when we are fitting that with the aircraft, it is subjected to distortion. So that's the reason why people now started thinking in terms of having the understanding of detailed inflow distortion at the time of design. That's what people they have done. This is what is one of the project for say counter-rotating fan, that's what is going on at European Union, that's what is between Siam, Russia, and say you are having DLR, you are having SNECMA, they all are the partners. Now what they have done, this is what is a facility, test facility at Siam, Russia. Okay. Now here if you look at carefully, this is what is a distortion screen what they have kept. What they have done is they have kept all pressure sensors at the inlet, okay, in conventional engine. They have flown that, and based on those captured data, they have artificially generated this distortion screen. And that is what they have used for the experimentation purpose. And what is their observation? Their design is in such a way that they are not having loss of pressure. So this is what is now new concept, what people they started talking of. If we are talking in terms of say challenging problems, like as I told, there is a possibility of deposition of your foreign particles. So there is a volcanic explosion in which there were so many particles they were flying, and that's the reason I think in the year of 2015-16 the whole flights, all flights they were stopped. Okay. What is happening? It is disturbing whole your compressor, it is disturbing your combustion chamber, it is disturbing your turbine. So here if you look at, this is what is my HP nozzle for the turbine, that is what has been covered with this as particle. Now the sticking of this particle, that is what is changing my flow physics on pressure and suction surface, that is what is prone to your rotating stall, and that is what is subjected to your surge. So that means this understanding is also required. Next challenging part what we are talking is in terms of bird strike. Okay, here if you look at, this is not artificially made, this is what is the real picture. If you look at what they have observed, this bird that will get just inside. So that will create the damage to the front blade. Immediately because of damage of this blade, whole engine will get into surge, and that's it, that's a failure of engine. Okay. Now here this is what is some other kind. So when you are flying at altitude, even during landing, even during takeoff, you need to be very careful of the bird ingestion. Now people they started designing the blades based on the concept, even you will be having bird ingestion, that will be having sufficient strain such that your engine will run for some time, okay, and you can have safe landing. Okay. This is one special kind of, let me run. Okay. This is one special kind of attention now. People they started talking in terms of high bypass ratio engine. What we are talking in terms of commercial engine, what is happening? Your bypass ratio you are increasing. Fine, you increase the bypass ratio. Now increasing bypass ratio at certain altitude, what is happening? You will be having ingestion of ice particles. What those ice particles they are doing? They are getting sticking up here in this particular region, say at the stator. No problem, let it do get stick up. After some time what will be happening? This rise of temperature that will peel off those layers. Now that is what is acting like a one body, solid body ingestion inside your compressor. And what it will do? That will do your engine to get surge. So there are so many failures of engine because of that. So now people they started talking in terms of this physics also. Okay. So this is also one kind of instability what we need to understand. Okay. So here if you look at carefully, this is what is happening. Now this is what is a strike, and then after just peel up of this, that is what is moving downside. Okay. One new concept what people they started talking, say over the year population that is what is increasing. Now everybody they want to fly. Now because of that requirement you need to have wide body aircrafts. Now this wide body aircrafts, what it says, my thrust requirement will be larger. So, if you look at this is what is my aircraft, say that is what is designed by say NASA. Here if you look at the engine, it is placed on the rear side purposefully because we are not having space to accommodate on the wing. Now, what is happening? My flow that will be entering all the way from my nose towards the downside. So, it will be having boundary layer that will be growing along the surface. Now, that boundary layer, that what is going inside my engine. What we have observed, what boundary layer or what disturbance, that is what is going inside my engine, that is what is creating trouble in my physics. So, here if you look at, this is what is their observation. What they say, this is what is a low pressure region, that is what is happening. It is an inflow distortion. Purposefully that is what is coming. So, now they started talking in terms of designing the blade in a different concept. That is what is distortion intolerant blades. Okay. So, the group from United Technologies and NASA, even for Rolls-Royce, Cambridge, they started working on this concept of boundary layer ingesting engines. Here if you look at, this is what is their reference blade. According to the requirement, they have modified that blade. Now, when we are modifying this blade and that need to care for your loading and unloading, that is the reason why what we are talking, they have shifted their CG position and they have modified their thickness, they have modified their incidence angle. Okay. Thank you. Thank you very much for your kind attention. So, now we have discussed in terms of say fundamentals of your axial flow compressor and flow instability in axial flow compressor, or what we say in terms of unsteadiness in the axial flow compressor. In the afternoon session, we will be discussing about say axial flow turbine.